Hi everyone, this is the third video for section 7.3 on multiplying and dividing decimals. So we're going to start this video by talking about the common algorithm for dividing decimals. So like all of these algorithms, we're not going to do any examples because this is something you do in your everyday life. There's plenty of examples in the book on page 268 for dividing decimals if you want to go and see it, but we're not going to talk about that here. So yeah, what does this algorithm say? So the first thing that we do is we multiply the divisor and the dividend. So both numbers in our problem that we're given. So for example, if we are tasked with doing the problem, if we're tasked with doing the problem 7.5 divided by 1.25. So if we were doing this, we would multiply both the divisor and the dividend by a power of 10 necessary to make the divisor a whole number. So we only want to divide by whole numbers. Okay, so in order to do this, we would multiply them both by 100. So this is going to be 750 divided by 125. So this was the smallest power of 10 we could use to make 1.25 into a whole number. So then we just divide this normally. So we know that 125 times 2 is 750. Oh, sorry, that is incorrect. 125 times 2 is 250, which is times 3 is 750. Sorry, that was hard for me to say. 125 times 2 is 250, times 3 is 750. So this is just 6. I don't expect you to be able to do that in your head, but for this purpose, it was easier for me to just do it in my head. So this is 6. And then we insert the decimal point in the quotient above the decimal point in the dividend. Well, I should have written this in a better form. So if we were doing 750 divided by 125, we would do 750 divided by 125, and this just goes in evenly 6 times. So the where you insert the decimal point is in the dividend, right? The number you divide by. That decimal point, after we divide by our divisor, we just put that decimal point right there. So this is 6 in both cases. So this is 6 and this is 6. So you just write it right up. So the mistake that I made here brings up a good point, is that whenever you're using this algorithm, you actually have to write the division sign and write it this way over here. You have to write it this way over here on the left for this algorithm to make any sense, so you need to write it this way. Okay, so why is it necessary in this algorithm to multiply by powers of 10? When we multiply by powers of 10, you can see what we did here. We just moved the decimal places a couple times. So the reason that we need to move these decimals is moving the decimals turns the division problem into a simpler problem. Where we divide by a whole number. So the whole point of this algorithm is to turn it into a problem where we divide by a whole number. And you can see that this algorithm does indeed make logical sense, because if we were to denote 7.5 and 1.25, that division problem as a fraction, it would look like 7.5 over 1.25. And then we would just multiply these by 100 on top and bottom whenever we move the decimal place. So this is 750 over 125. So we can multiply both the divisor and the dividend by a power of 10. And it just is the same effect as multiplying by 1. It doesn't change it at all, because if we write this as a fraction, it's changing our numerator and denominator by the same amount. So that's why these two problems are equivalent. And if you recall, whenever we talked about dividing fractions, we did something really similar to this, where the division algorithm for fractions didn't solve the same problem, right? When dividing fractions, you do the flip and switch, or however you'd like to think about it. But we also changed the problem here to an easier problem, where we don't divide 7.5 by 1.25. We end up just dividing 750 by 125. You can see that division has these tricks where we don't actually do the division problem we're asked to do a lot of the time. So we just kind of do an easier problem that has the same answer. Okay, so that is all I'm going to say about division. So now I'm going to talk about repeating decimals. So in section 7.1, we saw how to change a fraction to a decimal. And this only works if the denominator can be changed to a power of 10, right? We saw that whenever the denominator has a prime factor of 2 or 5, that we have this easy way to change it to a decimal, right? So the denominator, it only works to change a fraction to a decimal nicely if the denominator can be changed to a power of 10, which means the denominator has a prime factor of a 2 or 5 only. Only those two things in the prime factorization of the denominator. And this always results in a nice terminating decimal, right? We talked about a terminating decimal is just a decimal that doesn't go on forever, whereas a non-terminating decimal does go on. And that right, we have a terminating decimal and a non-terminating decimal, where the terminating decimal just ends at some point. Non-terminating doesn't end at some point. Another way that we can change a fraction to a decimal is to just divide the numerator by the denominator. So actually do the division problem that's implied by the fraction notation, right? We just did that up here, where we took 7.5 divided by 1.25 and wrote this division problem as a fraction because there's an implied division in fractions. So every fraction can be changed into a decimal by dividing the numerator by the denominator, but we may get what's called a repeating decimal. And it's a non-terminating decimal where something repeats forever. And so we have decimals that go on forever. For example, things like pi, right? 3.14159, and it just keeps going. So that's an example of a non-terminating decimal that's also non-repeating. There's no pattern to pi, and that's why mathematicians are so interested by it. It's because it goes on forever, but there's no pattern here. There's no pattern, and you can see that some of the examples we'll look at have decimals that repeat forever. And so this is we'll see it. We'll just go through the examples to see what I'm talking about. Sorry, I can get kind of I have a lot to say about things like pi as a mathematician. Okay, so we want to write each of these fractions as a decimal just by dividing the numerator by the denominator. So we are going to divide 5 by 8, and we're dividing whole numbers. So 5 has a decimal here. So 8 cannot go into 5 any times. So we're going to add a 0 here. Remember, we put our decimal straight above where it is here in our dividend. So 8 can go into 50 6 times because 6 times 8 is 48. And we have a remainder of 2. Okay, 8 can't go into 2, but remember that we can put as many zeros after 5 as we want. So this is 20. 8 can go into 20 2 times. 2 times 8 is 16. So we have 4 left. And again, we need to add another 0 here. Bring it down. So this is 40. And 8 goes into 40 5 times evenly. So there's no remainder here. So this tells us that 5 over 8 is equal to 0.625. Okay. So this one was a terminating decimal. And that makes sense with what we talked about in section 7.1, because 8, the prime factorization of 8 is just 2 cubed. So we could have gotten this answer using the strategies that we learned in section 7.1, but you could have also done it by dividing and gotten the same thing. Okay. So now we want to look at 7 times 11. Sorry, 7 elevenths. So we want to do 7 divided by 11. So 11 can't go into 7 6 times. So we have 66 with a remainder of 4. And then we bring down a 0. 11 goes into 40 3 times. So 33. And we get back 7 as a remainder. So at this point, you can actually stop, because at this point, when you get a dividend that matches your original thing, right? 7 was our original dividend. And now here we have a 7. So this process is just going to repeat. If we bring down a 0, 11 goes into 76 times with a remainder of 4. 11 goes into 43 times with a remainder of 7. And this process will just repeat over and over. There's no way that we'll ever get a remainder of 0. We're going to get a remainder of 7, and then a 4, and then of 7, and then a 4. And it's just going to keep going. So here we can notice that this process is going to repeat. So this fraction is equal to 0.636363 forever. And the way that we denote that is 0.63, and you put a line over the 6 and the 3 to denote that the 3 will be repeating. If you don't believe me that this is going to keep continuing like that, continue this division problem. See what happens if you pull down another 0 and divide 11 by 70 again. And just keep going, and you'll see that no matter what you do, you're just going to keep getting the same answers over and over again that repeat. So in order to avoid a problem like this where you aren't sure if the decimal will repeat, we have a strategy we can use to just look at the fraction and tell if you can tell if the decimal will be repeating. So we do this because when dividing two whole numbers, you will either get a 0 remainder, which is what happened here in 4A on the left. We eventually got a 0 remainder, or a remainder you've already encountered. For example, that's what happened here on the right, where we got a 7. Okay, so this is going to be the cases for a terminating decimal here on the left or a non-terminating decimal here on the right. So as soon as you come across a repeating number, so as soon as you have a repeating remainder, you have a repeating decimal. Okay. So like we talked about in section 7.1, you have a terminating decimal if and only in the case where your denominator only has prime factors of 2 and 5. Otherwise, you'll get a repeating decimal. And to tell what that repeating decimal is, you can stop as soon as you have a remainder that repeats, or you've already done that division problem. We've already looked at the division problem, 7 divided by 11, right? That's what we started with. So we don't have to look at it again. You can just say that it repeats. Okay, so this is how you can change a fraction to a decimal and look at repeating decimals. So in the next video, we'll start talking about scientific notation.